For decades, we've had this idea of what information is. We thought we had it all figured out. But modern AI, it's throwing a huge wrench in the works. It's showing us some massive cracks in our old theories. So today, we're going to dive into a pretty radical new idea that might just be the key to fixing all of it.
And we're going to kick things off with a question that, well, it sounds kind of impossible, right? Can an AI create brand new, genuinely useful information from basically nothing, just a simple set of rules? I mean, all our old theories would scream, no way. But what we're actually seeing in the real world, well, that's a completely different story.
And that right there, that's what we're calling AI's information problem. The theories we've been relying on for, 70 years? Think Shannon's classic information theory. They just can't keep up. They can't explain what we're seeing these amazing AI models do today.
I mean, just look at AlphaZero. This thing was given 0 human games to study. All it got were the basic rules of chess. That's it. And from that tiny, tiny starting point, it just played against itself and came up with strategies that blew past centuries of human grandmaster knowledge. So you have to ask, where in the world did all that new information actually come from?
And I love how the researchers frame this whole debate. They really hit the nail on the head. They said, look, when we watch AlphaZero, it's obvious it learned a massive amount of new stuff. But when we go back to our textbooks, our classic information theory, it tells us that's impossible. So something's got to give, right? The theory or the reality?
And that tension, that's our first big paradox for today. The paradox of creating information. It really seems like AI is just pulling new knowledge out of thin air, which completely goes against everything we thought we knew.
So the old rulebook has this thing called the data processing inequality. It's super simple. You can't get more information out of a process than you put into it. But the reality we're seeing with AI? It's the total opposite. We're seeing simple, predictable programs spit out this huge amount of new, complex, and genuinely useful knowledge. And this is a fantastic way to see it in action. What you're looking at are patterns made by something called a cellular automaton. All it is a computer applying the same simple rule over and over again. But check this out. Depending on which simple rule you pick, you can get these really simple, predictable, kind of boring stripes, or you get these incredibly complex, structured patterns, the kind of thing an AI could chew on for ages and keep learning from. Okay, so this chart basically puts some numbers to that idea. You can see a simple rule, it creates very little new information. No surprise there. Then you have a chaotic rule. It creates a ton of information, technically, but it's just random noise. It's completely unlearnable. But that third one, the complex rule, now that is the sweet spot. It generates a ton of new information, but, and this is the key, it's also structural. It's learnable.
All right, so that's paradox number 1. Now let's get to our second one, which messes with another fundamental idea we had. The idea that the order in which you get information shouldn't actually matter. So classical theory has this thing called the symmetry of information. It basically says that if you learn about topic A and then you learn about topic B, you end up with the same total knowledge as if you'd learned B first and then A. But come on, anyone who's worked with a large language model knows that's just not how it works in the real world. Trying to learn from a book by reading it backwards is totally different from reading it forwards, right? The order you feed data to a model can completely change what it learns. So this forces us to ask a whole new question. If the total amount of information is supposedly the same either way, why does the path you take to learn it matter so much? Does the order you discover things in actually change what you're able to learn at the end of the day? Well, the evidence says a big fat yes. I mean, check out this experiment. They trained AI models on chess games. One group saw the game unfold, move by move, and then saw the final board. The other group was shown the final board first and then had to work backwards to predict the moves that led to it. Now, that second task, the reverse one, was way harder. But guess what? The models trained that way actually performed better on totally new chess problems. The order didn't just matter, it made them smarter. Okay, so we've got these two huge paradoxes, right? How can AI create information from nothing, and why on earth does the order matter so much? Well, the researchers behind this paper propose a single answer, a brand new concept, a new way to think about information. And they call it Epiplexity. And here's the big idea. Epiplexity, it's the amount of structural information that an observer, and think of an AI model here with its limited time and processing power, can actually pull out of a set of data. The two magic words there are structural and computationally bounded. It's not about what's theoretically there, it's about what you can realistically learn. This really is the core shift in thinking. It means we have to stop asking how much information is in a dataset and start asking what kind of information is in it. Is it just a bunch of random noise, or is it packed with learnable structure? This visual just nails it. On one side, you have TV static. In the old way of thinking, that image has a massive amount of information, what we call high entropy. But it's just random chaos. There's nothing for an AI to learn from it, so it has really low epiplexity. But the animal photos, they're just packed with patterns an AI can latch onto. Edges, fur, eyes, shapes. They have super high epiplexity. Okay, that's cool, but how do you actually measure this stuff? Well, you can literally watch it happen while the model is training. So if you feed a model some simple, really predictable data, its loss, which is just its error rate, it drops like a rock and then just flattens out. It learned everything it could, really fast. But what happens when I give it data that's packed with epiplexity? Data that's super rich with structure? Well, now the model has to work for it. The loss goes down slowly, steadily, over a much longer time. And every little step in that downward slope, that's the model figuring out one more piece of the puzzle, one more part of the underlying structure. And that brings us right to how we can measure it. Intuitively, epiplexity is just the total work the model had to do. It's that whole area under the learning curve. You can think of it as a real, tangible number that represents how much structural knowledge the model had to soak up to really understand the data. Okay, so this is a really cool new theory for sure, but so what? Why does this actually matter in the real world? Well, the answer could completely change the future of AI development, especially when it comes to the most important part, how we choose our training data. Just look at this chart. Honestly, this is the big payoff. When the researchers actually went and measured the epiplexity of different types of data, the results were just, wow. Image data, like from CFAR, turns out it has very little epiplexity. Chess game data, it's in the middle, a medium amount. But then there's text, regular old text from the web. It has a massive amount of structural, learnable information. It's just off the charts. And this could be the answer to one of the biggest mysteries in AI right now. Why is pre-training on huge amounts of text so unbelievably effective? The answer isn't just about the quantity of the data, it's the quality. It's because text, as a data source, is just uniquely packed with aplexity. It's full of that complex, layered, learnable structure that AI models thrive on. So that leaves us with a really powerful, forward-looking question, doesn't it? As we're all racing to build the next generation of smarter AI, maybe we're focused on the wrong thing. Maybe the goal shouldn't be to just find more and more data, but to find data with more epiplexity.